Okay, so calculating equilibrium concentrations. So we've been talking about equilibrium, and remember that equilibrium doesn't mean that all the concentrations of the species are the exact same. It just means that they're no longer changing. Okay, and we saw that like in the graph, that very first graph that we looked at. So today I'm going to be introducing you to ICE tables, which just means initial concentration, that's your I, change, so how are they changing, that's your C, and then E is your equilibrium. Okay, what's your concentration at equilibrium? They just call them ICE tables. Okay, so for this, in a certain experiment, 2 moles of SO2, 1.5 moles of O2, and 3 moles of SO3 are placed in a 1-liter flask. At equilibrium, 3.5 moles of SO3 were found to be present. So calculate the equilibrium concentrations of O2 and SO2 and calculate Kc. Okay, so first off, they did not give us concentrations of the different species. They told us moles, okay, but they did tell us the volume as well. And remember, in order to find molarity, we just take moles divided by liters. Well, our liters are 1. So basically, we could just change all of the mole units to molarity. Because if we divide them all by 1, we then have molarity. Okay, so we do need concentrations in order to plug in. So a good chunk of the time, your volume will be 1, so really it's the moles or just the molarity. But sometimes it won't. Sometimes it'll be like 1.5. So then you actually have to divide to find molarities before you plug them in. Okay? So here's our balanced equation. We're going to make our ICE table. Okay? First, we're going to start with our I, which is our initial concentration. So we're going to write in our initial concentrations for each species. So for SO2, we have 2 moles, or 2 molar. For O2, we have 1.5 molar, and for SO2, we have 3 molar. Okay, our change is based on the way the reaction is going to go. We don't currently know which way the reaction is going to go. Okay. So we're going to skip change for right now. Okay. If you have 0 as a molarity for any of your species, automatically that means that it's going to flow to that side. The reaction is going to move to that side because it's got to fill that 0 basically. Okay. But here we don't have 0, so we don't know which way it's going to go. So let's fill in for our equilibrium concentrations. They gave us 1. They told us that SO3 is going to have a molarity of 3.5. Okay, so if we look at the change of SO3, did it increase or decrease? It increased, which means we shifted this direction in order to make more products. So this reaction at the initial, okay, if we were to calculate it, our Q would be less than K. It needs to catch up, so it needs to go forward. Okay, so now we can do our changes that are occurring. Okay, so because this side is increasing, we're increasing by a factor of 2 because of the coefficient. So we're going to have plus 2x. Okay, and we know that our reactants are being consumed in order to make products, so we're going to subtract. And we're going to look at the coefficients. So for SO2, we're going to have minus 2x. For O, there's no coefficient, so 1, so it'll just be minus x. Okay, so what happens is that this is basically just an algebraic expression that we need to solve for x, so that then we can plug it into these in order to solve for the final concentrations of our 2 reactants. Okay, so if I rewrite this linear, I have 3 plus 2x equals 3.5. Okay, so then it's just algebra. So I'm going to subtract over the 3 from the 3.5, so I'll have 0.5. Then I'm going to divide by 2. So my x is going to be what? 0.25. okay? So my x is 0.25, so now I can plug that into here. So I'm going to have 2 minus 2 times 0.25. And then for this, I'm going to have 1.5 minus 0.25. So this is going to equal 1.5 molarity, and then this one is going to equal 1.25 molarity. Okay, so that was step number 1. Calculate the equilibrium concentrations of O2 and SO2. We did. Okay, for our Kc, now we just have to plug in the equilibrium constants. Okay, so for our Kc, okay, first let's just write the expression. We don't have any solids or liquids, so we don't have to exclude anything. So we're going to have our SO3 to the second power divided by the concentration of SO2 to the second power, and then concentration of O2 to the first power. Okay, so that's just the expression that we've been practicing for all the different, or from the previous. Then we're just going to plug in these values, the equilibrium concentrations, into this problem. So I'm going to have 3.5, which is my concentration of SO3 squared, divided by my SO2 squared, so 1.5 squared, and then times 1.25. Okay, I ended up getting 4.36. Okay, it is a number larger than 1, so remember it does favor the product. So at equilibrium, we should have a higher concentration of products and reactants. If we look, we do. Okay, so that's our first type of ice table. So we were given the starting conditions for all of them. We're given the end concentration for one of them. We can do basically an algebraic expression to solve for x. Okay, for the next one. For type 2, we're given starting conditions and K. Okay, so we're not given a final condition. We have to use our K value to kind of help us to solve back through that. Okay, so it says, for the synthesis of hydrofluoric acid from hydrogen and fluorine, okay, now, synthesis means we're coming together, right? We're making hydrofluoric acid. If you don't know the chemical formula of hydrofluoric acid, if you look further in your question, it tells you, okay, HF, because hydrogen and fluorine are the H2 and F2 respectively, okay? So use your context clues to help you out. So we do need to write out the balanced equation for this. So we're going to have H2 plus F2 yields HF. So what do we need to balance? Just a 2 for our HF. Okay, we're going to have our ice table. To fill in. Okay, so they told us moles. This is in a 3-liter flask. So I need to divide each of them by 3. So what's the molarity of our H2 going to be? 1. Same thing with F. Okay, what about for HF? 4. Okay, so always be watching for that. Sometimes they'll give you the molarity. In this case, they give us moles. It is in a 3-liter flask, so we have to change that. So let's go ahead and fill in our initial conditions. So we have 1 molar, 1 molar, 4 molar. Okay? Now, we don't know which way it's going to shift. We don't have any ending equilibrium concentrations, okay? So now we need to figure out which way it's going to shift, which means we have to calculate Q. Okay, so for Q, we're going to plug in these initial concentrations, compare it to K, which is this number here, which is 115, and then determine which direction it's going to go. Okay, so for our Q, we're going to do products over reactants. So I have 4 squared divided by 1 times 1. So we're going to get 16.
Less than, which means forward.
Yeah, so Q is less than K, so it is going to go forward, okay? So I like to draw like a big arrow to show which direction I'm going. So I know it's going to shift forward, which means I'm going to subtract from the reactants, and I'm going to add to the products. So let's go ahead and write that in using the coefficients out in front. So I'm going to have a minus x from this one, or 1x, minus x from this, and then I'm going to have a plus 2x because of that coefficient on this side. Okay, so what we're going to get is 1 minus x, 1 minus x, and 4 plus 2x on this one. Okay, now we're going to plug these into our k. All right, so our k expression we know is hf squared over h times f, both to the first power. Okay, now we're going to plug in these expressions and the k value into this. So I have 115, I'm just going to change it to a regular number instead of scientific notation, is equal to my 4 plus 2x squared over, I'm going to do 1 minus x times 1 minus x, which is the same as 1 minus x squared, right? So I'm just going to write it as that because it makes it a bit easier to see what we need to do in order to solve. Yeah, it looks gross, right? But because we have squares in both of these, we can actually take the square root of both sides. So we can take the square root of the whole thing. Okay, so let's do that. So I'm going to get 10.7 is equal to 4 plus 2x over 1 minus x. Okay, so we do have to algebra here. Okay, I'm going to multiply over this whole expression, so the 1 minus x, so I have to do the distributive property. So it'll be 10.7 times 1 times 10.7 times negative x. So I'm going to get, I'm going to write it under here. So 10.7 minus 10.7x equals our 4 plus 2x. So from there, it's just a basic algebra problem, right? We just got to get x's on the same side and our non-variables on one side. Okay, so I would subtract over the 4, add over the 10.7, divide to get x by itself. So I had 6.7 is equal to 12.7x. So my x is equal to 0.528. Okay, so we found the change, but it wants us to calculate equilibrium concentrations. So all we got to do is take this and plug in. And then we'll have the concentrations for each. Okay, so 1 minus 0.528 will give me, I'm going to go ahead and write in a different color just so you can see this is our final answer. So 0.472 molarity. So that is the ending concentration once I've plugged in that x value. So same thing for this one, because it's the same expression. And then I'm going to do 4 plus 2 times my 0.528, and I get 5.06. Okay, so slightly different all the ones that I do give you in this situation, I will make sure that you can take the square root and not have to do nasty math algebra. Okay? Usually they don't give you nasty ones on the exams because you have limited time, so they don't do the ones where you have to do the whole quadratic formula. Okay. Last one. So we have our reaction here. Okay, 0.5 moles of A and B are placed in 5-liter container and allowed to reach equilibrium. Find equilibrium concentration of C. So let's go ahead and rewrite this equation. Okay, looking at this, are we going to include all of them in our equilibrium constants? No. Which one are we not going to include in our constant? B. So when we have a liquid or a solid in an ice table, we disregard. It's not important. It's not going to change anything to do with the shift of the reaction. So we just disregard it. Okay, so let's go ahead and fill in our initial concentrations. So it said A and B, which we don't care about B, is placed in a container and allowed to reach equilibrium. Okay, they said nothing about C, which we assume means that we started with no C. Okay, so right away, because we have 0 molarity for C, I know we're going to shift forward because there's no products to shift backwards. So I know we have to shift forwards. Okay, for my molarity of A, I'm going to take 0.5 divided by 5 liters. That gives me, 0.1. Okay, and again, we don't care about B. Okay, so because I know we're shifting forward, okay, that means that I'm subtracting from the reactants, I'm adding to the product. So I'm going to subtract 1x from the reactants for the products because of the coefficient. It's going to be plus 2x. Okay, so I'm going to have 0.1 minus x and then 2x. So now I need to plug it into the K in order to find the X to then find the equilibrium concentration. Okay, I highly recommend that you always write the expression first before you plug in the numbers, because a lot of times what people do, they'll plug in the numbers and they disregard this 2 up here, meaning that we have to square this. Okay, so if we look at just the regular, we would have C squared divided by, B is not included, so just A to the first power. Okay, then I plug in my information. It just helps to make sure that you don't forget any like squared or cubed that you might have to use based on the balanced equation. Okay, so now let's plug in the expressions. So my K is 4 times 10 to the negative 7th is equal to 2x squared divided by 0.1 minus x. Okay, now, in this situation, it's going to get yucky, right? Because notice I can't take the square root of both sides because this expression is not being squared like it was before. Okay, now, looking at this K value, it is very small. Very small. Which means there's not a lot of change happening. So we can ignore this. Because it's like subtracting 0.1 minus 1 times 10 to the negative 7th. It's not going to change it, especially with sig figs, right? It's still going to be 0.1. So we can ignore it. Now, very small is anything -3 or smaller. 3 and up in the negative direction, okay? Once it gets to like times 10 to the negative second, that can cause differences. They usually don't give you those. Usually they're very, very small so that you can ignore. Okay, so we're ignoring this, which makes the math much easier. Okay, so we're going to multiply over the 0.1, and then I'm going to go ahead and take the square root of both sides. Is that what I did? Yeah, I did. So I did 4 times 10 to the negative 8 when I multiply over the 0.1 is equal to our 2x squared. I take the square root of both sides to get 2 times 10 to the negative 4th is equal to 2x. And then I just have to divide by 2 to get that x is equal to 1 times 10 to the negative 4th. Okay, so that's my x, but if I look back at my problem, they just want me to find the equilibrium concentration of C. So I don't even have to plug it into this, which this one it should still be about 0.1. So I'm going to take this and plug it in here. To get that my concentration of C is equal to 2 times 10 to the negative 4th. Okay, so when you're looking at it, it looks like the algebra is going to be really, really gross. Probably you can ignore the x, okay, if you have a really, really small k. So really, really small k, you can ignore the x.